A right cylinder has a volume of 64 cubic centimeters. What is the radius of the cylinder that would minimize the surface area of the shape? Okay, so this is like the old, you have to make a pop can type thing at a factory and you want to minimize your use of materials type question. Imagine there is significantly more thought that goes into making a pop can than this, but it's an example. It's kind of cool. Okay, maybe. We'll see. So we want to find, you don't really know where to start. So what you do is you just start writing down every equation you think that kind of comes to mind. So we have volume of a cylinder. So you have a cylinder, probably looks something like this, and you're going to be like, okay, so that's volume equals the area at the top or the bottom, which would be a circle, which would be pi r squared. I'm going to multiply that times the height. What is the radius of the cylinder that would minimize? Okay. Pi r squared, and we know that that equals 64 cubic centimeters. Pi r squared. Yep. And then we know that area, which will be the area of the top, which will be pi r squared. Pi r squared for the area of the top. And that will be multiplied by 2 because we have both a top and a bottom. Then we'll have 2 pi r, which is the circumference. It's just coincidence that these kind of look the same. And that will be multiplied by the height. So you find the circumference of the base, or the top, and then you multiply by the height to kind of give you that hollow cylinder. And so we have two terms here. So now we want to rewrite these in terms of one value, i.e., I think radius? Radius. So we want to find the radius. We want to find some sort of equation that relates to radius. So what we're going to do is we're going to solve this top one for height and then plug it into the bottom one. The reason I chose the top one is because it only has one variable, or it doesn't have two things added together. If it had two things added together, it'd probably be a little bit more challenging to solve. And intuitively, I'm like, yeah, this one looks simpler, so we'll solve this one and then plug it into the other one. Might work out terribly, in which case we will basically backtrack and try again. So we say h equals 64. I'm going to drop the cubic centimeters. We'll just remember that, pi r squared. So move this over there. Okay. And so for area, with respect with a function of r, radius, we have 2 pi r squared, because that doesn't change. We have 2 pi r times 64 all over pi r squared, because that's the definition of h, based on our 64 cubic centimeters. Do a little canceling here. Got a pi that goes away, and have 1 r that goes away. So now we have a function that we're going to optimize, or in this case, I guess, minimize. So we have 2 pi r squared plus 64 times 2, which is 128. 128 over r. Okay? I'm going to rewrite this as r to the negative 1. That way it'll be easier to take the derivative. So we have 4 pi r plus 128 times negative 1 times r to the negative second, which equals, let's see, 4 pi r plus minus 128 over r squared, and we will set that equal to 0. Because when you trying to find maximum or minimums, you want to set it equal to 0, and that will be your critical points. All right, solving this for r, we'll find something like 4 pi r. We move this to the other side, 128 over r squared, and we get r cubed equals 128 over 4 pi. I wonder what 128 divided by 4 is. So 100 plus 28 over 4 pi, 4 over 4, 1 over pi. So I'm going to guess that this is, let's see, that's 25 plus 7, 32. So let's say 32 over pi. I should wolfram that. You guys probably have your calculators. But I have my wolfram. I could use a calculator too, but 30. It is 32. Why did I push enter? Sorry, wolfram, for making you do that extra work. So 32. So we are correct. So r cubed equals 32 over pi. Something more extravagant. We'll go with dark purple. Okay. So then, the optimal radius is the cube root of 32 over pi. Whoop. There we go. And, we even got that as a possible answer, which is nice. Now, how do we know that this is a minimum and not a maximum? Okay. So there's two ways we can do this. We can either reason it out by going to extremes. So if the radius was very, very small, like almost 0, then it'd be very, very tall, and it'd be a very inefficient use of surface area. So that's one way you could be like, that's probably true. Or we could do, let's see, 32 over pi, cube root over 3 is our critical point. And if we say that r is 0, so let's see, what's this answer going to be? So 32 divided by pi is like 10, and the cube root of 10 is like 2.5. So if we said that r is 1, so this is like, we'll write down here, kind of, sort of. So right in here is we kind of, sort of, a area of 2.5 radius. Yep. So it shouldn't be here because that's the, what is f of r? That's probably the area. That'd be, yep, we don't care about the area right now. It is what we want to minimize. But, nah, we're going to look at this differently. So we're going to look at this in terms of, so this is about 2.5. Go back to green. And so we'll choose like 1 and, I don't know, 4. So if we look back at our derivative, so 4 times pi times 1, which would be r here, so a prime of 1 would equal 4 times pi times 1 plus, or minus, 128 over r, which in case would be 1. This would be like 12 minus 128, which would be less than 0. Okay? Seems reasonable. So this would be negative. So it would be sloping downward. A prime of, all right, check this out again real quick. Make sure it's about 2.5. So 32 divided by 3.2 is about 10. Yeah, okay, I'm good with that. So a of 4 would be 4 times pi times 4 minus 128 over 4, which we know is like 32. This would be 4 times 4, which is 16. 16 times 3 is like 48. Yes. So we'd have 48 minus 32, which would be positive. So when we look here at our table, we have the derivative of r. This should actually probably be a, not f, because it has to do with area. So it goes down until we get to this almost 2.5 number, and then it goes up again So it makes sense that this would be the minimum. So to backtrack slightly, what we did, we're asked, all right, here is a volume of a cylinder. So we wrote down, all right, so we know this is the equation for volume, this is the equation for area. We used the set volume that they gave us to rearrange and find a value for area, like the surface area of it, which we knew is the top circle, the bottom circle, and the cylinder around the sides. We rewrite it like this. We then take the derivative of that, so we find the surface area with respect to the change in R. We then set that equal to 0 to find a critical point. We got this crazy 32 over pi cube root number, which is almost 2.5. And we knew that was going to be a critical point. It's either going to be a maximum or a minimum. And intuitively, we pretty much knew it was going to be a minimum. But if you find something like this on an AP test, you have a free response type question, I just go with it. Be like, yep, minimum confidence. Because you really don't have time to go through all the checking that we did. And so to check it though, we drew out our table and we're like, all right, to the left of 2.5, this crazy number, it's decreasing. And to the right of this number, specifically at 4, it's increasing. And we plug this into A prime of R. And since we get kind of this down and then up motion, you're like, oh, well, right there, that's probably going to be a minimum. We also could have plugged in a number into area and then found that if we plugged in numbers in all of these and we say, okay, this number is the smaller than the other two, then that's another way we could do it. It's just that in this case, I think it was easier to work with the derivative than it was to work with the area with respect to R. Specifically because I didn't want to plug in this into an equation. It just looked tedious and difficult. Anyway, so for a while we've known that this was the answer, and so that's going to be the answer. That's the general kind of path you do for these optimization problems. You don't know what to do to start with, throw up as many equations, create a single equation if you can, take the derivative, set equal to 0, test for max or min. And that's the general idea. Thanks much.